I'm going to demonstrate the Parasoft C, C++ test capabilities for software improvement in the embedded software domain. Capabilities that we're looking here will be those that involve cross compilation to a target's platform, support for bare metal or embedded systems, custom workflow, and the Parasoft tool's capability to be integrated across several popular embedded IDEs such as Eclipse or Visual Studio for that matter. The demonstration here can be done either in a Linux or a Windows machine. If the two pieces of software that needs to be installed, first is the cross compiler. If you're using a Windows machine, you can download the cross compiler from this link and unzip it to a location of your choice. If you are using Linux, then also download it from here and unzip it to a location of your choice. You need to edit the activate.sh to point to the path where you unzip the cross compiler. So the steps that I'm going here can be reproduced by anyone who has an installation of the Parasoft C, C++ test, as we'll be using a virtual ARM target in this demo. So once the cross compiler has been unzipped, the next piece of software that you need to install will be the Chemo emulator. If you're using an Ubuntu, this command here will install Chemo in your machine. If you're using Windows, then there's a link here where you can get the installation of Chemo for Windows. So after these two pieces of software is installed into your development machine, let us clone this project first. You'll notice here that I'm using get bash in my Windows machine here. So Windows users, you need to install get bash. After that, after making adjustment, I already installed Chemo in my laptop here, as well as the cross compiler. Now I will source the activate.sh. After that, the cross compiler shall be made available in my terminal. So you can see that I unzip it in drive D, and this particular cross compiler has a version of uh, Linaro 750. But first, let me describe what the folders mean here. The entire example project is located in the src folder. So these here, all the files of the project. Then the rest of the folders are support folders. For example, the Parasoft is where I put the custom compiler here, as well as the recipe template here. Now, this demonstration can be done on an actual hardware. An example of an ARM64 target would be a Raspberry Pi, but we'll be using the virtual hardware here in Chemo. So now that I've cloned the project, I'll go to the chemo folder and boot the virtual target. I'll be selecting item number 2 here as the older Ubuntu 16 has an incompatible C++ library. It can still work, but it's not as smooth um, as we want it to be for this demonstration. So I'll just select the second here, which is compatible C++ library. I will pause this recording and resume when the download is about to complete. When the boot.sh has completely downloaded the target image, it will boot the target image. It usually takes around 3 to 4 minutes for the virtual ARM64 target to fully boot up. So let us give it some time. I will open a new terminal here. I will pause the recording for another 2 minutes and resume after that. Try to log in into the target. So usually this permission denied happens when the target has not fully booted up. So let us give it a few more seconds. So the password here is in the README. And after logging in inside the target, we're going to create this destination folder inside the target. Let's log in again. Okay. We're asked for the password. Now we are inside the ARM64 embedded target. I will now create the destination folder inside the target. I will exit and then I will create an SSH keygen key pair. Since I already have this key pair here, I will just proceed to the next step, which is to set up a passwordless SSH access into the target. Now, succeeding logins from here on should no longer prompt for a password. This is very important because the Parasoft C, C++ test unit test workflow in this demo shall use the SSH as a target as a transport mechanism. Let us exit and log in again. And indeed, we are not being prompted for a password logging in. So I'll go now into the location of the project into the SRC folder. It is a makefile based project, and to build it is just to type make In order for Parasoft to understand the structure of the project, it has to insert itself in the middle of building the project. You can see here that that is done by intercepting the CC and CXX make variables. This is the cross compiler, and the Parasoft CPP testcan utility inserted itself at the front of the cross compiler and specifying a CPP testcan BDE file to be generated. So let us try to type that command. But before running the make command, I like to make it known that the CPP test scan is available in my terminal here, and it is located in this path here. If such is not the case in your system, then you need to set up your path environment such that the CPP test scan is immediately accessible in your terminal. I'll remove the comment and run the make command. Now that the build has completed with the Parasoft CPP to scan in the middle intercepting the CC and 6X, the binary is built, and at the same time, a CPP to scan BDF is generated. The BDF file should list all of the C++ code base that is part of the project for code analysis. Now that the BDF has been generated, I will open the Parasoft IDE. You can also use an Eclipse IDE with the Parasoft plugin installed. Here, I'm just using the default Parasoft Eclipse-based IDE. As with anything that is using Eclipse, project has to have an associated workspace. I will write that workspace in this path here. Now, we have the IDE loaded. The Parasoft uses definitions of the EDG compiler front-end standard in the expression of language support and compilation capabilities. The creation of a custom compiler project, other, C++ test here. So the creation of the custom compiler is a step whereby a particular C++ compiler not directly in Parasoft's list of supported family is brought into its closest compatible definition, basing off from existing definitions in Parasoft's list. I'll choose the import as I already have these definitions here pre-created in the repository. GCC tool ARC64. So you can see here that the Lenaro ARM64 7.5.0 is brought to the definitions of GCC12 ARM64 that is already in Parasoft's list. Finished. Now let us load the BDF file. Click the Create a Project, select C++ Test, create project from a BDF data file. The BDF file is in the src folder from where we build the source code. Open that and load it into the IDE. This dialog is expected that it cannot be detected as we are going to manually select the custom compiler to be used in this code analysis. Now, the custom compiler that we imported a while ago should be selectable from this edit box here. At the top, you should see my Kimo arm. So this is the custom compiler based on GCC 12 ARM64 that we imported a while ago. Select it and click yes. You will notice that these three fields here have been changed appropriately. Click finished. And now we have loaded the project into the IDE. A successful static analysis, the automated generation of unit test cases, the production of an instrumented binary are often an indication of a matching custom compiler definitions. Now, the successful execution of this binary to emit the expected results, test, and coverage log files could still require additional adjustments. So let us try to do static analysis first. I will choose effective C++ as this is a C++ project. We are not seeing any errors. We have a successful static analysis. We are not going to dive deep into the static analysis portion, so I'm going to delete the results that we have here. So now let us proceed to the second part, which is dynamic analysis. First, I have to generate the automated test cases here by right-clicking SRC. Select Generate Unit Test. The test folder has been created, and let's try to, for example, we have an addnum function here. Let's try to pick how the addnum function test cases have been auto-generated. Go to Test Case Explorer, and we can see 10 instances of odd num. The first instance is using 43 into the parameter and the max limit of an integer and calls into an odd num. The second test case is using 0 for the B and maximum for A. So you get the idea that there's a heuristic in which the test cases have been generated. Clearly, the 43 here is reflecting the fact that the logic of the function has uh, has a 42 as a constant. So the generation of these cases is trying its best to be creative in how these cases have been generated. And that is, it looks into the implementation of the function under test. Now, if this have been host-based testing, then right now I could right away click here, Parasoft unit testing built-in unit test, and it would build an x86 binary and execute here in my development machine. But as this is an embedded system development where the execution needs to run and to happen on a target of a different architecture, we don't have that capability here right now. And furthermore, there are other steps that is required to to be performed in order to run the test. So this additional step we need to import as the additional XML workflow template. So I prepare this template, go to Parasoft test configuration in the user defined import, and Parasoft user defined this one. The unit testing can be done in actual hardware. You can see here the Raspberry Pi would be a prime example of an ARM64 target. We don't have that right here. Instead, we have the Chemo version. So I'm going to import this one to match the Chemo that we have now. Open, and then select the execution tab. You can see here the target has a value of on localhost 127.0.0.1. We can see also the target test directory. This was the folder structure that we prepared inside a target a while ago when we were able to log in inside. We mkdir this exact path here. We have the username and Ubuntu. But the exact granular detail of what's going to happen can be seen if we open the XML file here by clicking the edit button here. New embedded systems development IDE can passively have in its menu system all the necessary workflows to accommodate the various setup and steps, mostly especially in embedded systems domain with constantly evolving and different cross compilers and hardware target properties and characteristics. Depending on the characteristics of the target device where the unit test is running, different communication transport mechanisms are possible from serial to TCP/IP, and the target device may not even have a file system to store these test results, in which cases Parsoft has a flexible listener to fill up in this gap. Take some time to familiarize the structure of this XML. You will notice, for example, the SSH there is a variable that gets reused down below here. So the flow of this recipe template is sequential from top to bottom. First is the cross compilation of the binary. Second would be the custom step in sequence. First, it's being copied into the target using the scp command, and as expected for an scp command, the port is required here, which is 222, indicated by capital P. After that, the custom recipe template changes the permission of the binary in the target to be executable. After that, the binary is executed, run in target using SSH again as a transport mechanism. It should generate CPP test results that test log and coverage log, to which we copy back these generated log files back to the IDE as well as the coverage log. So you can see here that these are the way of Parsofts handling the various different ways in which embedded testing is executed. I'll cancel this, closed. Now that the custom workflow template for the chemo is imported, right-click into the SRC folder, test using, select user-defined, embedded systems run, test, and chemo. The exact steps can be viewed in the console tab. You can see here the uh, compilation of the runtime source of Parasoft to get built into the cross-compiled binary. And now we're seeing the part where the cross-compiled binary is being copied into the target. Now it's being changed permission and then executed. This is the output of the executable, and the test results back copied to the IDE, and we have a successful unit test here. This can be seen from the code coverage log. The details of which can be exactly seen in the coverage tab here, 93% total, per file, and per function. Now, if we go back again to the and log in into the target, and we can see here that the test exec made its way in this location just as how the recipe template is being scripted. And as it is executable due to the csmod that we see in the XML workflow. So since we're here, I'm curious, let me go into the folder here. And let me manually run test exec. So this is the output that we saw in the console log here. Here. And if we check the file, we can see that the coverage log and the test log have been generated. And part of the XML workflow is to copy this coverage log on test log back to the machine and then delete it from the host. You can see here in the XML workflow recipe, the step, the last step performed is to delete the log file, remove file step, and that is why we did not see these log files when we logged in. As we manually executed the executable here, so this file we can see being generated. So what we have seen here is Parasoft's capability to integrate into complex embedded workflows because of its EDG compiler front-end definitions and the custom recipe workflow to express in XML the needed necessary steps that needs to be done in your embedded testing and setup. Thank you for your time and uh, have a nice day.